Massimo, okay.
Okay, so now we'll have a talk from Tomas Vitvar. Tomas Vitvar is currently associate professor at the University of Prague. I met Tomas, let me know a personal note, when about 20 years ago we met exactly in this hotel giving a tutorial on semantic web services that we built. It reminded was the time of the semantic web service movement. Tomas was one of the members of the DERI, I think Galway-Wisbrook, right?
It's Galway.
Yeah. Galway, in which they, probably many of you remember, in which there was the famous Wismo, Wismix, Wismif. Right? I remember still of them. And we met Isat in this order at that time to make a tutorial on different approaches to service composition. We were in the Roman model that was a bit different, and then we tried to match. From then on, Tomas had his career before in Innsbruck, then he moved to industry, and now he's in Prague, where of course he will become very soon to higher level, as every one of us. So I'm very happy that he will give us this talk, probably different from the previous one, so let's move to theory to practice, I would say, right? Good.
Okay, thank you very much for a nice introduction. Hello everyone. I would like to give you a talk about an interesting topic, which is from legacy to Kubernetes, the SOA transformation. And it's really interesting because there are two kinds of architecture principles that we're trying to meet here. One is the monolithic architecture. So when we say the service-oriented architecture, it has a specific meaning, especially in terms of the architecture as well as the technologies. And then we have Kubernetes, which is a new architecture that started to emerge not quite some time ago, a decade ago, say. And it's a completely different concept. And obviously, now if people are building services, they are building applications, there's a push that they need to build the applications to be running in Kubernetes. So they build it as microservices. So that's what is happening. And also, when there is a need to actually make changes to existing applications or to legacy applications, then what they usually do is that they basically start from scratch. Because it's very difficult to move a monolithic application to Kubernetes, because the Kubernetes provides certain features when it comes to scalability, deployments, reliability, and these kind of new things that the Kubernetes provides do not really work well with the traditional architecture. But the reality is slightly different, because I worked in the industry for many years, and I work with large customers, and I work as the integration architect, so I'm kind of in the core of the architectures that the main responsibility is to actually integrate applications. Then I can see that it's not easy for them to actually start from scratch, because they have large customer bases. They have customers that could be like over 1 million or 2 million or 5 million. And their business support system stack, which supports the business operations, is large, and they cannot just throw it out and start from the beginning. So they have to have some kind of path where they can start using the new technologies like Kubernetes with the existing architectures. So this talk is about this. So how we can actually move from the traditional SOA architecture to Kubernetes in phased approach. So I don't know how much you are aware of these basic principles that are currently available in the cloud-native computing foundation, so because it's a suite of technologies that you can use, but also there is an underlying architecture. And there are technologies provided by the operating system at the container level. So I would like to first very briefly discuss what these technologies are. So what is the container, basically, because this is at the bottom of everything. And then I will talk about the Kubernetes. So I will introduce what the Kubernetes is, and very briefly. And then I will use these kind of things that I will talk about later when talking about the service-related architecture and SOA transformation. So in the first part, I will talk about cloud native. Then I will talk about the service-oriented architecture. So what it is. I know that everybody understands, but I think that we need to kind of remind ourselves, because it's kind of maybe old thing, it's a legacy thing already, and we just need to understand what we mean by the service-oriented architecture. And then I will talk about the SOA transformation project, and later I will conclude. So, as I said, whenever an organization wants to move to Kubernetes, so there's basically two options. So the first option is that you start from scratch, you start building your application as microservices, then you start using the cloud-native technologies like Kubernetes and other related technologies, and you are done, right? I mean, that works if your application is small and you can do it that doesn't have much impact on your customers. But Cloud-Native Computing Foundation has this nice trail map, which says basically that you should do your transformation in a phased approach. And the first thing you can do is the containerization, which means that any process you have or any application you have, you can actually run as a container. So it doesn't mean that this application must be a microservice application. It's an application, it's a kind of process that you run in the operating system, and you can run it as a container. There's no problem with that. Later, what you should introduce into your process is the CI/CD, which means that you want to automate the deployment, you want to automate the testing, and basically continuous integration, continuous delivery, also with help of the tools that the Cloud-Native Foundation provides. And then you may start orchestrate your applications or services that are running as containers. So basically you start using something like Kubernetes. Obviously there is much more than Kubernetes or more technologies as Kubernetes, but Kubernetes is the leading platform that is promoted by the Cloud-Native Computing Foundation and that is provided as an open source platform to run your workloads in Kubernetes. So, and this is exactly what we did. So when you have a monolithic application that you basically cannot throw out and start from scratch, we need to first start to containerize it, which means that we have to basically run the application processes as containers, provide the container images for the application file system, and then start using CI/CD, run the deployment processes and testing and everything on top of the images that we provide for that application. And later you can introduce Kubernetes. So we exactly follow this path, and I'm going to talk about more details about it. So, as I said, at the bottom of everything is a container. The container is a kind of term that everybody is now using when talking about the cloud native and microservices. But I think we need to understand what the container actually is. So in this figure, you can see that we have a virtual machine, or it could be a bare metal or virtual machine, that really matter. Then there is a operating system, which is the host operating system. And what is important here is that the operating system supports Linux namespaces. So any new modern operating system that you currently use, which is the kernel version, the latest version 5.6, is actually supporting 8 Linux namespaces. And the Linux namespaces is the important feature of the operating system that actually makes the container a container. Then you have a file system for your container, which is basically a layered file system where you have different layers that you can compose together. And on top of that, you run your containers. So when your container is running, first it's a process, which means that this container is isolated on a number of Linux namespaces provided from the operating system level. But then it's also running on top of the file system, which is provided as a container image. Now, there is a nice kind of thing about that, because you can actually share the container image across multiple applications that are running on top of it, and they can share the different layers from the container image. So there is a really big optimization when it comes to the container image and the part of the file system that the image provides to individual applications. So for the container to be able to start, you basically need Linux namespaces, but then you need these things here, which is the container runtime, container engine, and then you have a client that interacts with the container engine using the API over the TCP socket or the Unix socket. And the client, everybody probably knows, and you've probably tried it out already, when you start a container using Docker, you basically run your container. So you are basically operating your environment using the Docker client, talking to the container engine using the Unix socket or TCP socket, probably Unix socket, because we are on the local host. and then you are basically managing all the thing. So this concept is exactly the same for anything you are running in the environment. So if you have your host running your system, or you have Kubernetes and you have a worker node on the Kubernetes in the worker node, that's exactly the same thing. So, but the client in this case would be Kubernetes, which is a component running in the worker node, talking to the container engine and basically operating that node when it comes, to the requirement to start the container, stop the container, or do some kind of operations in the container. So, what are the Linux namespaces? As I said, the version, kernel version, Linux version 5.6, there are 8 namespaces. There's a number of namespaces, which is a kind of, you can understand the namespace as a kind of isolation level, but the process is running in the operating system. So we have mount namespace, UTS, IP, CP, ID, network, user, C group, and time. All of them are very important, but what is actually very much important is this network namespace, because we are dealing with the distributed systems, and obviously service-oriented architecture, the individual servers running in the service-oriented architecture are servers running in a distributed environment, so they need to talk to each other. So we need to be sure that we can talk to each other, the applications can talk to each other smoothly without any issues. But the problem here is the network, because they are isolated on the network. So what it means is that when you start a process as a container, using the container runtime, the container runtime will automatically create isolated namespaces in all 8 groups for this process, which means that the process will be isolated from other processes at these levels, which means that the process will not see each other. So we will have a process, it will see, for example, the process ID, but it will see only its process ID and the process ID of its children, but will not see the process ID of other processes running on the same host. So this is the isolation that the Linux namespaces provide. And the same is true for example, network. I will comment on the network in a bit moment. So you have a process, it's running in 8 isolated namespaces, and then this process can start a child process. And if the process starts a child process, the child process automatically is started in the same set of Linux namespaces as the parent process. You can also start a sibling process of that process, and it will also be started in the same set of namespaces. So you can actually kind of organize how you want to run your processes and in which Linux namespaces you want them to be running. You can also choose the namespaces for your process. So you can, for example, say that all namespaces will be default, which means that the process will start in the default namespaces. The default namespaces are default namespaces provided by the operating system. But for example, you can choose only one network namespace, one namespace, for example, network namespace that you want to be isolated. And this way you can basically organize your processes in a way that, for example, you can start 2 processes, they will share the network namespace so that they will be able to communicate with each other. But no other process that will be started in the network namespace will be able to communicate with these processes. So there is a lot of things that you can do with this. And obviously you will not be able to, you will be able to operate the containers at this level, but you are not probably going to do that because this is where you use the APIs and the tools provided by the technology. So what I'd like to comment here is the network namespace. The network namespace is very important because, as I said, if you have multiple applications running on the network, they need to communicate with each other. And the problem could be that they cannot communicate because they are on the different networks, right? So how actually the network namespace works? So when you start a process in the network namespace, which is isolated for this one process, what happens is that network stack will be created for this one process. So by the network stack, we mean interface, routing tables, and sockets. What it actually means is that the process will only see its own interface, which is dedicated for this one process. So in this example, in the container, that container has an interface Ethernet 0, and then this container is running on the host, and on that host is also the Ethernet interface Ethernet 0. So these are 2 different interfaces. This Ethernet 0 is the interface in the dedicated network namespace for that one container, and this Ethernet 0 is the network interface on the host. And now if you want to connect the Ethernet 0 on the host and the Ethernet 0 in the container, there is a technology or the container engine actually creates this virtual Ethernet bridge and connects these two interfaces together. Plus, it establishes net filter rules so that the routing is actually possible. So then you can expose the TCP socket on the virtual Ethernet bridge or on that level, and you can let the communication to actually be possible between the host network interface and the container network interface. So this is the principle how it works, and this is very important because what is actually happening if you start a container in the Kubernetes, later I will show some examples, then you will always have the container running in the overlay network, which means that it's a dedicated, separated network from the rest of the world, and you will need to manage, or the Kubernetes needs to manage this kind of connectivity. And this is very important, and there are specific network protocols that I'm going to mention later that are actually struggling with that. And these protocols are actually coming from this legacy applications, where, for example, you have this monolithic application using RMI protocol, which is the leading protocol in Java, and these protocols actually issues using or connecting via the interfaces in here. So let me give you an overview of what actually is Kubernetes. So at the bottom of everything is the containerization. So you have these containers, Linux namespaces, containers available in the network, but the Kubernetes is a kind of orchestrator that is built on top of this. If you look at this architecture of the Kubernetes, which is the standard architecture that you can actually find on the internet, there are two kind of components of the Kubernetes. So one is the control plane. The control plane is the set of services that is responsible for managing the Kubernetes cluster. And then you have data plane. And data plane is a set of worker nodes. So this is where your workloads is running. So for the worker node to be able to connect to the Kubernetes cluster, there needs to be a couple of components. So there is a kubelet component, which is actually a kind of component that manages that worker node and connects everything which is running on that worker node to the Kubernetes cluster. And there is this proxy, which is managing the network connectivity. And there is a couple of components in the control plane, like a database, etcd. There is an API server, because obviously you can communicate with the Kubernetes cluster via the API. You can manage everything through the API. So there is this kind of command line interface that when operators are talking to the Kubernetes cluster, they are using kubectl, which is nothing else than the API invocation of the specific functions on the API server that you can actually manage the whole thing. And then there is this important component here, which is the cloud control manager. Because when you start a Kubernetes cluster, you can obviously start it in your on-premise environment. You have your own data center, you can install it, it's open source, there's no problem. But most of the setups that you will come across will be cloud setups, which means that the Kubernetes service is provided as a service from the cloud vendor. And that's why there needs to be a tight integration between the Kubernetes service and the cloud provider. And this integration is very important because the cloud provider is providing the additional services from the cloud, like, for example, load balancer, that allows you to actually talk to your workloads running in the Kubernetes cluster. And this link is actually managed by the Kubernetes. So whenever you are creating a specific resources, so that you can, for example, expose the connectivity to your clients using the external IPs, this connectivity is actually built by the Kubernetes when you create these kinds of services, which is a service of type of balancer that you need to create to be able to actually make the connectivity possible. So now I have a kind of simplified picture on the Kubernetes cluster, just to explain a couple of basic concepts to understand how everything works. So whenever you want to run your application in Kubernetes, you will basically define your workload. So there are several types of workloads that you can choose in Kubernetes. So one of the most probably used ones is the deployment or a stateful set. So there are some few differences, it's not much important now. But basically what you do, you define your application as a deployment. In the deployment, you specify the containers that your application is composed of, that you want to run in your Kubernetes. And then as a result of it, if you create or if you install this deployment in Kubernetes, there will be pods created. So now we have additional terminology here. So we're talking about the containers, so we already know what the container is. The container is nothing else than a process which is isolated on a number of Linux namespaces in the operating system. But now we have another terminology which is a pod. The pod is nothing else than a set of containers, and the principle is that the pod can run one or more containers that share the Linux namespaces. So this is what the pod is. So whenever you talk about the Kubernetes, you many times come across a term like a pod, but basically it means that you run some kind of an application in a container. So these kind of terms like pods and containers are sometimes used interchangeably. So when you install this deployment, as a result you will have pods created in your Kubernetes cluster. And now there is this important concept. So the Kubernetes is actually, the technology, it's a platform that when you decide to run your application in Kubernetes, so what you do is that you know what kind of application you want to run. So you know your application. You know that the application has, for example, application logic layer, it has a database, it has a kind of backend, right? So this is your application. You have your components to run your application, but you do not care about where the application is going to run. This is the basic principle, that the Kubernetes will take care of your application to be running in the cluster, and you don't care where the application will be running. And this separation is actually made possible because of the containers and the isolation, and mainly because of the container network interfaces that the Kubernetes provides. So what actually happens is that you have your deployments. In the deployment you define what you want to run, what is your application, and then you tell Kubernetes that you want to run this application. And the Kubernetes will start the application, and you do not care where it is running. What you care about is that you want certain instances of certain pods, right? So for example, say, okay, I want 5 instances of pod 1 and 3 instances of pod 3 or whatever. And the Kubernetes will make this, will try to actually achieve this requirement with respect to the available resources, and different kind of parameters that the Kubernetes observe about the Kubernetes cluster. So now you have your application running as pods. You don't know basically where they are running, and you don't need to care. You can find out, but maybe you don't need to care about that. But now another requirement is that you need to be able to access your application. And for that, the Kubernetes defines a resource, a Kubernetes resource, which is called a service. And using the service, you basically define the mapping between the external client that want to access your application and your application running in the Kubernetes pods. So another important point is that whenever you run your deployment, your application, the layout or the topology of the application in the Kubernetes cluster can change. So for example, you decide to run one more pod because you want to kind of address the additional requirements for the load. So you decide to increase the number of instances of your application, or the Kubernetes somehow decides, or maybe there is a failure of a worker node, and the Kubernetes basically move that one pod to another worker node. So there could be a change in the topology. So the services actually are built in a dynamic way that, or they are defined in a dynamic way, and they basically say that, okay, I want to access my application on a specific TCP port because this is where my application is available, and I want to include all the pods using a specific selectors, like a rule that the Kubernetes selects for this service to actually include in the service. And this is done automatically, and of course this could be reconfigured on the fly. But at the end, what you have is that you have an external endpoint that you can access your application on a specific TCP port. Now, what is really important here is that the Kubernetes is a very flexible system. So you can actually expose your services on the worker node's IPs. Because one thing that I would like to also mention here is that the worker nodes here, like worker node 1, 2, and 3, they have their IP addresses. These IP addresses are available from the outside, so they are typically routable from the client side. They could be routable, so they are external to the Kubernetes, and they are entry points to the worker nodes. However, And what you can actually do is that you can define your services that these pods will be actually available at the worker node IPs. But this is not a good practice, because what may happen is that the worker node IP will suddenly fail, and the Kubernetes will reshuffle the pod and will move it to another worker node, because there is a requirement that needs to be 1 or 2 instances of that pod running at any point in time, so the Kubernetes will move it to another worker node. So if your client is actually dependent on a specific configuration that will access your services on a worker node IP that will not be available, that your client will fail. So from this reason, what is actually a good practice is that you should expose your connectivity to the pods running in the Kubernetes via the services of type load balancer, and that is an automated kind of link made with the load balancer provided by the cloud. And that cloud is the external IP that the client will then connect to. So this is the integration between the Kubernetes cluster and the cloud where the Kubernetes is running. This load balancer here is external to Kubernetes, and it's designed to be active-passive, which means that whenever it's running on multiple nodes, there is a floating IP address, which means that if one node fails, that floating IP address will be automatically moved onto another node, so that the load balancer is always available and the client can connect to it. So this is very important, because if you define your cluster, if you define an application running Kubernetes, you need to always respect this principle that the application is actually hidden from a network perspective in the overlay network. The overlay network can be anything. It doesn't really matter where your applications are listening inside the overlay network, but what really matters is how this application is accessible from the outside. And this link is really important to achieve that requirement. So this was really like a very brief about the Kubernetes, because I kind of had to discuss that before I going into the details of what we actually did and how it actually was working. I think it would not be really clear if I talk about that without this information. And now I would like to talk about the service-oriented architecture. And first, I would like to say something about the architecture's evolution. And in that process, I will explain how the actual architectures evolved towards the microservices. So now we know what we can use to actually run the microservices, and where it fits the service-oriented architecture, where it fits the other principles that we work with. And then I will talk about the enterprise service bus. So enterprise service bus is the integration middleware that is in the core of the service-oriented architecture that integrates the applications in the environment in the service-oriented architecture. So I will start with this very nice kind of picture, which kind of shows 3-tier client-server architecture that is a typical architecture for any application today, where we have presentation layer running on a thin client like a browser. Then we have application layer, application logic provided by the application server or the web server. And then we have a data layer where we have a database, right? Very clear, no problem with that. The important thing about this, so if you look at from a historical perspective, so these layers, especially the application layer and the data layer, they're like monolithic systems, and they are still there. So we still deal with these applications, and as I said, that if people want to move to Kubernetes or to microservices, what they probably do is they will refactor these applications. They will throw them down and start from scratch and build them as microservice architectures. But they are applications still that we are using. It's a monolithic systems, monolithic applications, and I will try to comment on what the actual monolith is and why it is important to know what the features of the monolith are when you want to move over to Kubernetes. There is quite an important thing here that, this kind of architecture, so if you have many applications like that, and you want to integrate this architecture, the applications with other applications, you probably, if you do not do it correctly and properly and according to the SOA principles, you will end up in the spaghetti integration, which means that you will basically do the point-to-point integration, and you will have quite a lot of mess in your integration architecture. And this is happening, and basically there was a response to this, which is the service-oriented architecture that I will later show. So This architecture has been kind of enhanced a bit because obviously there were requirements for the scalability. So we want to have the middleware like load balancer, reverse proxy that would be able to distribute the load across multiple instances of the application in the cluster. So there is this middleware layer that actually was introduced. But this middleware layer could be pretty much many kind of technologies you can use at this point. You can use, as I said, the scalability, middleware like load balancer, authentication or authorization service, but also integration middleware. So this is where we kind of meet this architecture with the service-oriented architecture that I will show in a moment. What actually we still see here is there are still monoliths, of course. So all these layers are monolithic applications, and there is still this deployment overhead, and that kind of comes from the fact that we are dealing with monoliths, and there are scalability and performance issues, of course. And now we are in microservices world, right? So what it actually means for the microservices is that you are kind of putting everything together, right? So you are breaking down the functionality of the monoliths, and you are creating a set of microservices, and you are basically having a single, many times it's a single Kubernetes cluster where your microservices are running. So you have, I call it backend here, which is basically Kubernetes cluster backend, and then you have middleware, application server, as well as the database, everything in one node. So this is what is actually happening now, and many microservice architecture are built like that. So this is the evolution where we are now, and everybody is kind of heading. Of course, on the client side, there are also kind of components, so you can also decompose the functionalities into components that could be somehow linked with the microservices provided at the backend layer. So, as I said, we use Kubernetes to run these workloads. There could be large Kubernetes cluster. There could be also multiple Kubernetes clusters that are interconnected with each other. So there are different options. But there is a kind of like a step in between, right? So as I said, we can actually, what we can do, we can throw the application out, start from scratch, build the microservice, and it will end up in that architecture that I was showing before. Or we can do a kind of intermediate step, which means that we will look at our multi-tier architecture, and we will say, okay, we can still use new principles and new technologies to run our applications, which means that we somehow define the components of the application, which are not microservices, so but we use different color here. So I kind of depicted it here as a set of servers, so they will be more like a set of servers, and we want to use the Kubernetes to run those servers. So which is a kind of step where we first containerize those applications, and then we can use Kubernetes to run those applications. So I call it like not a microservice architecture. So, and it's very confusing because to many people, when you speak about the Kubernetes and microservices, so whenever you use Kubernetes and you say, okay, I'm using Kubernetes to run my application, the people automatically thinks that this application that you run in Kubernetes is actually microservice architecture, but it's not true. Because the microservice architecture is really the architecture that is defined by the application, not by the Kubernetes. Kubernetes doesn't care what you are running in Kubernetes, right? In Kubernetes you can run whatever you want. But if you run your microservice architecture in Kubernetes, that's great. You can really use a lot of interesting features that Kubernetes provides you. It was built to run the microservices, but nobody will stop you from running anything in Kubernetes. And this is exactly what I would like to point out here, that in here, what we are doing is that we are actually using the application monoliths as they are, because we cannot change them. It's very difficult. We have large customers, we have large workloads, we have large performance. We cannot just throw it out, but we want to move towards Kubernetes. So that's why we are using these features of Kubernetes and run the applications in Kubernetes. And you can gain a lot of improvements from this process. So we have improved deployments because now we are using container images. We have improved failover because now the application is running in Kubernetes in the Kubernetes cluster. If one node fails, then we will move to another node, and it will just Kubernetes will take care of it. So there is a lot of advantages. So now as I was talking about, this first kind of architecture where we have three-tier client-server architecture, and it leads to the spaghetti integration. So this is a typical kind of architecture where you would end up with if you do not do it properly. So basically, you are starting to integrate application in ad hoc way. You say, okay, I want to integrate this application with this application, I will do it, then another person will do exactly the same for different applications, and you end up with something like that. And this was the situation before the SOA technology, like maybe 20 years ago or 15 years ago, and that's why the organization started to look into the service-oriented architecture, because they wanted to have a kind of organization in their integration architecture. So how the service-oriented architecture from a very high-level perspective, very simplistic view looks like is that you have applications. They all provide nice interfaces, typically, in the SOA world, because the SOA is very much attached to the technologies like web services, SOAP, BPOL, and these kind of technologies, XML. And they are nicely connected to something which we call the enterprise service bus. The enterprise service bus is the integration middleware that provides the connectivity, and it allows to integrate the applications in the integration processes that you define in BPOL, and they are running in the in the enterprise service bus. So this looks very nice, and when the salespeople were selling the service-oriented architecture technologies to customers, it looks really great. And say, okay, now we will have everything nice, shiny, great service-oriented architecture that solves all your problems in the world. But the reality is slightly different, because if you look into the details of this, then you will see that there are spaghetti inside. And that's because one of the main kind of activity that you do within the service-oriented architecture, within the enterprise service bus, if you define the integration processes, you do the data transformation. So you need to basically transform the data from one format to another format. So for that, there are specific tools, typically based on the XSLT in this enterprise service bus environment, and you're mapping one format to another format. So you do it one-to-one, right? And this guy will end up in spaghetti again, but the spaghetti will not be as visible as before. The spaghetti will be inside here, inside the data transformations that the enterprise service bus is using. And that's a kind of clutter that again you have to deal with, but there is a response to it, which is the common data model. The common data model would probably solve the issue, but it's only a theoretical kind of view, because the common data model is very difficult to build for large setups, right? Imagine that you have 50 applications here, and you want to build a common data model for all. It's impossible. And now we are with the microservice architecture, so that's another kind of step in evolution. So in here, you see a typical today microservice architecture as you can actually build, and you would build if you do it this way. And again, you have spaghetti here, right? So we are back, I call it like back to the Stone Age, because we are kind of having spaghetti again, as we wanted to avoid. So we introduced a architecture. Okay, we kind of fixed this problem. Now we are moving towards microservices, and we are getting spaghetti. So, because there is no really kind of way how we can actually introduce kind of organization of this. Because what you see here is that there are different kinds of services. There are kind of mixture of the platform services. So the services that would normally be provided by, for example, the integration middleware, like the data transformation, orchestration, or whatever. And business services, right? So it's a mix of things together. And so this picture is actually from the real world project that has been built for a number of years, maybe 2 years. It was a kind of startup in the Czech Republic, and they end up with something like that. And it was a big clutter. So there is obviously a lot of discussions whether microservice architecture makes sense, because to some extent it may not really make sense that people, because they are building it today with a big effort and big enthusiasm, they are basically creating a microservice whenever they think there should be a microservice, they are creating this microservice, and sometimes it doesn't really make sense. So it's much better to actually group the microservices to large blocks sometimes and make it a bit more organized. Okay, so if I look into the enterprise service bus, so what it actually is enterprise service bus, because this is what we are kind of doing, right? So in our project, we were looking into the transformation of the service-oriented architecture to Kubernetes, but because we are dealing with a large environment where we have over 50 applications, you cannot actually transform every single application in one go to Kubernetes, or to use the Kubernetes as the platform to run the applications. So we focused only on one element, which is the core element of the architecture, and which is this enterprise service bus. So if you look at what the enterprise service bus actually is, so again, there is a view. So we had this kind of view on the service-oriented architecture with the enterprise service bus in the middle. But now if you look what this enterprise service bus is, you actually see that the enterprise service bus is built on top of the application server. It is running as an application in the application server, and it is a distributed environment. And this is a kind of legacy architecture where you have a cluster, and the cluster is nothing else than you have multiple processes that are running in the cluster. So they are kind of, they replicate the objects that they provide to the applications. And this is how it is. So they are running on 2 nodes. For example, this is the example where we have node 1 on a certain IP. And these processes here are basically listening on the IP address of the node, right? So there was no issue with the connectivity, because when you have an application talking to the server, then you are basically talking directly to the IP, which was routable from the client side. So there was no problem. So there was no overlay network. Obviously, there are different network layouts that you need to actually make the routing possible, but the routing of the overlay network didn't come from the application architecture. So the application architecture was running on the same network as other clients running on that network. Now, if you look at this one box here, which is the application server instance, then you can actually see all of this here, right? So there is a number of layers of what the application server actually is about. So, and this is the view, if you look at it from the operating system perspective. So if you go to the box and you will list all the processes, you will see a process, and that process would be a JVM process, but it's not very simple, because that JVM process would have multiple layers that you would obviously not see from the operating system perspective, because in there you would just see one process. But if you know the architecture, how it looks like, then you will be able to actually understand what is in. So you have a JVM process, then there is a number of Java technologies. And I forgot to mention that most of the enterprise service buses today on the market and in the past were actually Java-based. So this is also somehow in line with what I said, that the XML is kind of coupled with Java a lot. And so this is the reality basically. So you have many different vendors providing this kind of application server technology, including Oracle WebLogic, SAP NetWeaver, you have IBM WebSphere, JBoss, for example, from Red Hat, which is open source. All of them are based on the Java, so it's the same thing. So we have the Java technology here, for example, RMI, which is very important protocol for the Java, and it's very interesting because this RMI protocol is a specific protocol which is Java dependent, right? So if you want to communicate with an application over RMI, then you need the client to use the libraries from Java to be able to communicate using RMI. So this is a big problem, because this is not technology agnostic, this is really technology dependent, and it causes a lot of issues. So obviously, if you want to run your application and expose some kind of functionalities of your application to your clients, you would use HTTP, right? Which is technology agnostic protocol that anybody can connect to, no matter in which environment the client is implementing. But for the RMI, it's not the case. You have to be Java-based. Your application needs to be Java-based. And there is other technologies that is in the stack. Then we have application server kernel, which is a kind of core. And on top of that, you have a number of services. But by the service, I mean like a platform service, which is a service provided to application running in that application server instance. So for example, there could be a data source. Like you can have a connection pooling, providing by the data source that the application can use the connection pool to get the connection to the database, so that they don't need to establish the connection separator, but they just get the connection and talk to the database, which is for the performance issues that you want to fix or when you want to deal with. There is a JMS server, very important thing, because most of the integrations are asynchronous based on the JMS, and that's why you need these JMS technologies here. storage forward agents, other things. And then you have the application, right? So if you look at this stack and the enterprise service bus, and try to understand what actually the enterprise service bus is, it is nothing else than the application running in the application service stack on top of all these layers. And this is what actually, when I say monolith, so this is the monolith, right? And the monolith is monolith because there's a lot of different components that are bundled with that package. And there is also a lot of dependencies across the components. So there is, for example, dependency between a service running in ESB on the data sources provided by the project server, by the application server. So this is just the example. I don't want to go into much detail because I think I don't have much time, but this is just the example of a real-world process. So if you say there is a process in the enterprise service bus, it's the integration middleware, then this process is actually running, integrating a number of applications in the environment, and this process can be decomposed to a number of flows. And in here you will see the flows with different components. I don't want to go into the details, but in here I can explain some of the dependencies as I was talking about. So how typical processes are composed on the ESB. So you have at the application server layer, you can have resources, right? So this could be a thread pool or connection pool, for example, some kind of an application. Now you have services defined in ESB. So these services are like a box of functionalities that you can reuse in your processes. So there could be a service like a JMS consumer that accepts a message from a client, like a JMS message, if you want to do the asynchronous integration. Then there is a DeepL process service. This is actually an orchestration running, doing some kind of data transformation, etc. And there's many more. And now what you do is that you compose those services into a more complex processes that are then become processes in the ESB that the clients can involve. And what I want to highlight here is that these services are actually using the resources, and there is a dependency, right? So you can have a service 1 using the resource for the thread pool, and then you have service 3 using exactly the same resource, which actually means that if you run instances of these two processes, they share the same thread pool in the application server. So which means that, if there is a thread pool of 30 threads in the pool, then you can only run 30 instances of process 1 and process 2. So these kind of dependencies actually make things a bit more difficult in the application server, because you also have to make sure that there is you maintain a kind of relationships between the different resource constraints that you define. So for example, in this case, there is an error because in here you have a connection pool for the downstream application, which is only 20 connections. But in here you have 30 connections in the pool, which actually means that if those processes are running more than 20, these processes will fail because they will not get the connection from the pool. So these kind of dependencies across resources are quite important that you need to maintain and be able to resolve. And basically during the design time, you need to understand how the dependencies look like and how they should actually look like. Okay, so now going to the last bit, the SOA transformation. So what we did, we were working in the BSS stack. The BSS stack is a business support system stack, a lot of applications in the stack with the integration middleware. The integration middleware was quite big as well because there were so many applications. The integration middleware was actually defined in 5 integration domains. It was a very large customer base, so over 10 million customers. 500 services altogether, and with a performance demand of 100 requests per second per service, so which is quite a lot. So we really, the middleware altogether had to kind of maintain this kind of performance demand. And what we did, we actually used exactly the same approach that I was showing before. So we are kind of preserving the same architecture as coming from the monolith itself, but we are using the Kubernetes to run the servers of the application. So this is the view on the architecture, how it looks like. So basically we have, at the Kubernetes level, we have these resources, which are basically pods running in the Kubernetes cluster as pods. They are providing connectivity using the load balancers through the load balancers provided by the cloud. And there are kind of two kinds of connectivity, because the issue is that, as I mentioned, this RMI protocol, it's a complicated protocol. I have one more slide on that I would like to also show, is that this actually makes issues when you connect when you try to connect a client using the load balancer, and the server is actually running on the overlay network, which means that it's listening on an IP which is not routable from the client perspective. So there is a specific configuration that you have to put into place to be able to make it working. It's not as nice as shiny HTTP protocol, because with the HTTP protocol we can actually make this much better. So there is a standard setup of the ingress and the load balancer, and everything is working without any issues. So let me just show this slide here, which is this one that I would like to mention regarding this connectivity, because I just started to talk about that. So if you have an RMI connectivity, the RMI connectivity is actually about two things. So first, you have a client that needs to look up so-called stop. So it needs to basically find the service that he wants to talk to. What happens is that it finds the stop of the service, and the stop is transmitted over to the client. And then the client is using the stop to talk to the server, to the skeleton, right? But the issue here is that if the server is listening on the private IP that is not routable from the client, it gets the stop, and the stop tries to call to this private IP. So this connectivity will never work. So you have a proxy IP, so we have a proxy, TCP proxy in between, and this connectivity will never work. So that's why there is a solution for that you basically need to expose the proxy IP on the definition of the service, so that the client knows, or the stop knows, about this public IP and can talk to this external IP. So this is one more kind of step that you need to introduce into the architecture to be able to talk to something which is behind the proxy. So this proxy, it's a kind of representation of an entry point to the Kubernetes cluster. So you can imagine that this is running a Kubernetes cluster in the overlay network on the IP addresses, which is not routable from the client side, but this proxy actually makes the connectivity possible. And there is a routing in place, but the client needs to know where to connect to. And so that he knows, he gets this information from the stop and from the specific configuration that we introduce. There is also one more issue related to the autoscaling, because when I mentioned that people are thinking that when they run their application in Kubernetes, it automatically becomes a microservice. But this is not true, because as I said, you can run anything, but the microservice is actually coming from the application architecture, not from the Kubernetes platform. And people also think that they can auto-scale, because this is one of the selling points of the salespeople. If you talk to them and they say, okay, you can use Kubernetes to run your application, there will be auto-scaling automatically possible, so you will be able to save costs. You will be able to save costs because you need to run so many applications, so not many instances, because your demand for the application is not so high, so you can just reduce the number of application instances, and when the demand is high, you can start more applications up. But this is very difficult to achieve, and the reason why it is difficult to achieve is because there is a dependency of different resource constraints that you have inside the enterprise service bus. So for example, in this example, we basically have two resource constraints. So one is the threads that you run your application processes. So in this case, there are 4 threads that could be like 4 threads running. And then there is another resource constraint, which is a kind of pool that you need to get the connection in order to be able to talk to the external system, right? So in this case, you are talking to some kind of external system. You need to get the pool token, the token from the pool, and then you talk to your downstream application, sending some kind of data. The problem here is that if you scale this up, then you are basically increasing the resource constraints on all levels automatically, because it's a monolith. So you are adding more instance, you are basically adding more resources into the pool as well as to the number of threads that you have available here. So, and that's a problem. So this is the reason why you cannot automatically scale up, because there is a dependency on the downstream application. So for example, if you have a certain amount of tokens in the pool, then this application is actually relying on that. So there are some certain resources allocated for the number of tokens that you have in this pool. And if you start to increase and then decrease, then it will make a problem. So if you want to scale up, you want to add a server to the cluster, you need to do it with respect to all other backend applications that exist in the system. So this is very difficult to achieve, and this is impossible, right? So that's why the topology of your application, even if it's running Kubernetes, must be running with a fixed kind of topology. And if you want to add servers to your topology, then you need to do it with respect to the requirements of the backend applications. Okay, so there is one more thing, which are also quite interesting, because sometimes you have applications which are desktop, and you need to access them running in the containers. So this is a kind of solution that we built for that. And finally, the conclusion. So what I would like to repeat, what I already said, is that it's important to actually apply the phased approach. We were able to actually start using the CI/CD correctly to build, deploy, test, etc., and use Kubernetes as the platform running the containers. There is a lot of advantages that we can gain. So first, it's a step towards Kubernetes, right? So if you start to introduce Kubernetes to your environment, then obviously you have a team who are aware of the Kubernetes. They can learn how to operate the Kubernetes, and they are ready to introduce additional applications, maybe with the microservices into the Kubernetes cluster. So it's very important to just start introducing these technologies in a phased approach so that they can start using them gradually. And there's obviously a lot of challenges that I mentioned: networking, technology-specific protocols. There is also deployment challenge, because in microservice world, you normally deploy your applications to the Kubernetes cluster as new kind of versions, and the versions are coming from the container images. But in the monolithic applications, like for example Enterprise Service Bus, the deployments actually sit in the DB, so your container images are useless for that. So, but you can still use the container images to distribute the software for your service. So that's an advantage. And challenges regarding the running the old-style applications like desktop. And obviously, as I said, we need to preserve the USB topology to be able to run it smoothly and without any issues. Okay, thank you very much.
Yes, we are a bit late. I think that we have time for a couple of questions.
You don't need the mic.
You don't need the mic. Okay. Yeah. So questions? No questions. I have a couple of comments then. They are shy. The first one is that I'm very happy to see you provided us very complete application. I'm very happy to see that it's still everything based on Java.
Yeah.
According to the youngest in the other, not me, now it's vacated, let's say. They will program in Python to sustain that Python is the future. So I'm very happy that still Java is playing a big role in industrial application. And the second comment is that, in my opinion, a very interesting effort. We have very concrete cases that are difficult to find, is to see how the model that we had seen yesterday about composition of components within 2000 can be applied to this type of architecture. Because I think that in that case it would be very interesting to exploit the properties that they presented to see if automatically you can refactor the application on the basis of the compositional effort.
Yeah.
So I don't say more because I have an idea that we will come
Sure.
But I think that this is what in the community is useful, that we see how to apply theoretical models down to concrete cases in having a real engineered approach to software.
Yeah.
That is what personally I miss a little bit in the last days, let's say. There was many years ago, but now is with all these machine learning stuff, we are losing then the software engineering part of our job. And I like that from the theory to the practice, we can try to decompose that. My opinion is my 2 cents. That's it. Have a good lunch, and we see you at 3 with the Lupe.